Hi, my name is Corey Lynch, and today I'd like to present some of our current research involving advancements in the methods used to calculate ionic conductivity of solid electrolytes. Previously, we have researched some properties of a family of experimental and theoretical borsite and thiourea-borsite solid electrolytes. We were able to determine their ground state structures and study their stability with respect to their decomposition space, as well as in contact with pure lithium. Some of the ground state structures are shown here for the experimental compounds. So to continue our analysis of these materials, we had hoped to investigate their performance by estimating their ionic conductivity. Unfortunately, we ran into computational bottlenecks with the ab initio MD simulations, and we were only able to qualitatively assess their performance. Looking at the lithium positions over time, superimposed on the ground state framework, we were able to see that the lithium seems to be diffusing well through the crystal. So here are two examples which showcase this lithium diffusion within a borsite on the left and a thiourea-borsite on the right. So in order to estimate the conductivity, typically we would assume that the ionic correlations are negligible and just use the tracer approximation for the conductivity, which is based on the mean square displacement of the ions. A recent paper, however, by Marco Longo has shown that for highly correlated materials, this is not a good approximation. If we instead calculate the full conductivity with the Green-Kuba formalism, we will have a much better estimation. Unfortunately, the ionic correlation effects typically show up at macroscopic timescales, which would require much larger MD runs than we can do. There has been a lot of interest lately in machine-learned interatomic potentials, which involve using some machine learning method to learn a potential function from structures generated from this ab initio MD. These predictive functions output structural energies and atomic forces from given input structural configurations, and they claim to offer much better performance than the DFT while retaining the accuracy of the DFT. There are many different methods contained in this machine learning field, but neural network implementations are some of the most popular. Baylor and Perinello showed in 2007 that a basic neural network can be used to great success by accurately predicting the radial distribution function of silicon and showing good agreement in structural energy prediction between the DFT and their neural network method. So Allegro is a newer, more sophisticated neural network machine-learned interatomic potential, which was developed by the MIR group at Harvard. It uses a graph network architecture with strictly local message passing layer updates between atomic pair embeddings. These embeddings are defined using equivariant tensor product representations of the group of 3D rotations and translations. Allegro is shown by the authors to have very good MSD trajectories when compared to DFT for lithium phosphate, which is shown here. Allegro models ran in labs were also shown to have excellent hardware scaling and performance, reaching nanoseconds per day of performance. So in order to assess the feasibility of using Allegro to generate long MD simulations, which we need to estimate ionic conductivity, we decided to start with a simpler material than our boresites, which has smaller unit cell and fewer atoms. We decided on this lithium silicate phosphate alloy, which was based on the work by Dang and others, showing this alloy to have good lithium mobility. The structure we chose was a 25 to 75% ratio of silicate to phosphate, which is shown on the right. When running long MD simulations, we must consider the inherent Lyapunov instability, which results from an accumulation of integration errors. So as described in Frankel and Smith, these errors result in exponential divergence of trajectories when starting from the same initial conditions. So here we see that even in a 10 picosecond simulation that was ran on different hardware architectures, the lithium trajectories are already diverging. So one way to help mitigate this issue is by using a block method of averaging the MD simulation data, which is shown here on the right, and this method was prompted by helpful correspondence with Griselli. This block method ensures that each time interval is averaged with the same number of samples of that interval length from the MD data and gives better statistics. From some preliminary MD data, here we compare the block method to a simple method for averaging MD intervals. So the simple method is just averaging every interval of a given size possible across the MD data, which therefore has an inconsistent number of samples from each interval. This results in poor statistics, since the largest interval, for instance, will have just one sample, and the smaller intervals will have many more samples. So here we do see that the block method is producing more linear MSD trajectories compared to the simple method, which does suggest that the block method may indeed be helping to mitigate some of this instability. Now we go to our testing of Allegro. So we tested Allegro with many different hyperparameter choices to determine which settings to use that would give us the best trade-off between accuracy and performance. Our Allegro model was trained using ab initio data from 600, 900, and 1200 Kelvin runs with the settings shown here on the left. We used 300 training and 30 validation structures, which we sampled from a total of about 6,200 MD structures. And here we see that the mean absolute errors for the energies and atomic forces on the training data are excellent, about 0.3 millieV per atom for energy and about 2 millieV per angstrom for the forces. Here on the right, we plot the structural energies for DFT compared to the Allegro predictions for all 6,200 MD structures, most of which were not included in the training, and we see that they are in excellent agreement and that Allegro is extrapolating well to these untrained structures. Here we see the preliminary results of comparing MSD trajectories from Allegro models ran in LAMPS to the ab initio trajectory at 1200 Kelvin. The LAMPS models were ran at 3 different block sizes, 85, 170, and 340 picoseconds, and each block size was ran with 4 different initial velocity seeds. This resulted in a total of 12 different LAMPS trajectories, which we compared to the original MD trajectory, which only ran for about 14 picoseconds. So on the left, in the short time range, we see that the LAMPS model's MSD trajectories are in excellent agreement with the ab initio MD trajectory that they were trained with. On the right, we see that in the long time range, if we extrapolate the ab initio MD trajectory linearly, these LAMPS models are still giving reasonably good agreement in the long time frame. Unfortunately, there is a bit of divergence in the trajectories of the long MD runs. So next we compare the calculations of the tracer approximation with the full conductivity. Again, we're using the same LAMPS runs we saw previously with 4 MD runs per block size and a total of 12 MD runs. So we see that the full conductivity paths in blue are somewhat smooth, but they're still not linear as expected, and they still do not converge at long time scales as desired. So although there is more work to be done on the full conductivity, we do see one promising behavior, which is that overall the full conductivity is larger than the tracer approximation as expected. So our future plans involve finishing the current investigation into the feasibility of using these new methods to calculate the full ionic conductivity. Some things we haven't yet looked at are different statistical methods besides just the block method, and we also haven't looked at the effects of cell size on the MSD. So 2 recent papers by Griselli address these issues. On the left, we see a result of their study of finite size effects, where they show that the cell size of various materials does make a significant difference in the resulting MSD trajectories. And on the right, we see a result of a study of a new spectral method of statistical analysis, which does a good job of reducing the noise and error of the full conductivity calculation. So we hope to apply these new methods to study our boresight materials and accurately predict their conductivity. So in conclusion, our preliminary results are very promising. The Allegro architecture does a great job modeling the data from MD simulations, yielding low structural energy and atomic force errors when compared to DFT. The performance of the Allegro model in LAMPS simulations is excellent. We're easily able to reach the nanosecond range of simulation time for a 132 atom simulation cell. The long MD runs we see with the Allegro potentials are extrapolating well from the ab initio data for the MSD, but there is not yet convergence on the full conductivity. So we may need better approaches to take into account the Lyapunov instability resulting in this divergence at long MD runs, which may include newer statistical methods, larger cell size, and possibly also more MD runs with more variety in these initial velocity seeds. So to conclude, I'd like to say thank you for listening to my talk, and I would like to acknowledge all of the support behind this research. I'd like to acknowledge my advisor and collaborator, Dr. Holdsworth, Chuan Wei Tan for his Allegro support and correspondence, the MIR group as a whole for their development and support of the Allegro software, Dr. Griselli for correspondence regarding the computational methods, and of course the NSF, Wake Forest University, and the DEAC High Performance Compute Cluster for their educational, financial, and compute resources and support. Thank you.